Hello and welcome to a ramble with me. We're rambling about IEB's May 2025 paper 2, question 9. In the diagram below, triangle XYZ is inscribed in circle center O. Inscribed meaning that all of these vertices are lying on the circumference of the circle. The radius of the circle is r units, so I see a radius OX, I see a radius OZ, all of those have length r, and XZ is p units, angle Y is theta, and we're asked to prove that sine theta is equal to p over 2r. I have no idea where to start. We don't have any right angles, so SOHCAHTOA is not really optioning, right? Begging on. Sorry. The next best thing in my mind is to use the sine rule, so we know that sine theta over p is equal to, say, sine z over this length is equal to sine x over that length, right? I don't know. Then we have the r's over here. I don't know what the r's can do for us, but they're there. There is this angle at center relationship here. So this angle is 2 theta. We've got the r's, we've got the p. We're asked to show that sine theta is equal to p over 2r. Well, we know that cos 2 theta, we could do something here with the cosine rule, right? So we know that angle O is equal to 2 times angle Y, and that is because angle at center is equal to 2 times angle at circumference. Okay, so that would be 2 theta. Okay, and then we know that OX is equal to OZ is equal to R because they're both radii. So I'm going to fill that in as well. Oop. Right. And then using the cosine rule, so the cosine rule says this guy squared is equal to this guy squared plus this guy squared minus 2 times this times cos of that. So let's put that down. So p squared is equal to r squared plus r squared minus 2 times r times cos 2 theta. So that is 2r squared minus 2r squared cos 2 theta is equal to p squared. We want to end up in a situation where the trig ratio is by itself. So I'm going to factor out the common 2r squared here. And we're just left with 1 minus cos 2 theta. Please don't minus 2r squared and 2r squared, right? 2r squared belongs to another term. Okay, so we can't just randomly minus it from here as though it does not have a commitment to cos 2 theta. So the more correct thing to do would be to factor out the common 2r squared in both terms. Right, and then we can divide both sides by 2r squared. And so we've got p squared over 2r squared is equal to 1 minus cos 2 theta. So that's already looking quite good, right? Because we've got p over 2r, this is p squared over 2r squared. Like, that's, I don't know, that feels like we're going in some direction. So let's have a look here. 1 minus cos 2 theta, we want to end up with sine, so I'm going to express this using this expression of the cos double identity. So 1 minus 1, those will cancel out, and then we've got minus 2 sine squared theta. So this is 2 sine squared theta is equal to p squared over 2r squared. Okay, and then we divide both sides by 2. Okay, so then this is just the same as p squared over 2r squared times 1 over 2. Right, so that is p squared over 4r squared is equal to sine squared theta, and so therefore sine theta is equal to the positive square root of p squared over 4r squared. Why are we not considering the negative square root? We are not considering the negative square root because this is an acute angle. Yeah, this is an acute angle. So the sine ratio will be positive. So if we square root the top and we square root the bottom, we wind up with p at the top and 2r at the bottom. And that is exactly what we set out to prove. So this is one of those questions where it's like the serendipity kind of serendipitied. Yeah, this was kind of the breakthrough connection, and I don't know how, I feel like there's just something about seeing this shape that is so angle at center-esque. The same way that if I were to see this shape or this shape, or what's another one? How else does it appear? Yeah, those are the, this is, yeah, this is the one we just saw. How else does it appear? Angle at center. That's pretty much it, right? Like, yeah, this one isn't really different to this one, quite the same, but you know, oh, I guess the really popular one is where it goes like this. You know, where you just see those shapes and it's just like, it's go time, man. It's angle at center. And those are things that come with doing lots and lots and lots and lots of practice. So that is the key takeaway, is to train, you know, that visual muscle, that visual memory, bank as many things so that, you know, it just gives you a nice bed of things to try in a situation like this where it's not immediately clear where to start. Right, let's see what the memo has to say. The memo is interesting. Whoa, let us dive right in. So the memo starts out the same as me. We start by indicating that this angle is 2 theta because angle at center. Then it says XZO is 90 minus theta because these two sides are equal, they're radii, and so added together these angles will be 180 minus 2 theta, right? Angle sum in triangle. And then you halve that because angles opposite equal sides are equal. So if these two add up to 180 minus 2 theta, then each of them must be 90 minus theta. Okay, so I'm just gonna write that down. So, wow, that is not convincing. Let's try that again. So we have here 90 minus theta. Okay, and then what happens from there? Riveting stuff. Then they say sine 2 theta over p is equal to sine of 90 minus theta over r using the sine rule. Very nice. And then they kind of just simplified from there. So let's just do that quick. So they say sine 2 theta over p is equal to sine of 90 minus theta over r, right? And sine of 90 minus theta is just the same as cos of theta. And then this side we have 2 sine theta cos theta over p. Can divide both sides by cos theta, right? So then you have 2 sine theta over p is equal to 1 over r. And then we can times both sides by p and divide both sides by 2 in order to get rid of this guy. And then you're just left with sine theta is equal to p over 2r. How elegant, how absolutely beautifully elegant. I love that. Absolutely love that. I love that more than my solution, honestly. So that is another way you could have gone about it. So yeah, let's leave it at that and see you another time for another ramble.